All right, so looking at slide 22, this shows graphs of the revenue, cost, and profit function. So the graphs of the revenue and cost function are shown on the right. At X values where revenue is above cost, there's a profit, and where revenue is below cost, there's a loss. Okay, that should make logical sense. So the height of the profit function at any X is the amount by which the revenue is above the cost in the graph. All right? So, since profit equals revenue minus cost, and if we differentiate each side of the function, okay, so profit equals revenue minus cost. If you take the derivative, you have the derivative of profit equals the derivative of revenue minus the derivative of cost. And setting that equal to 0, we can see that the derivative of revenue is equal to the derivative of cost to maximize that profit. All right, so the last equation can be expressed in marginals, which we did a couple of sections ago. And that's the classic economic criterion for maximum profit. Your maximum profit exists when your marginal revenue is equal to your marginal cost. Okay, there's another one to add to your list. Your marginal revenue equal to your marginal cost gives you maximum profit. All right, so let's try an example. If a farmer has 1,000 feet of fence and wants to build a rectangular enclosure along a straight wall, if the side along the wall needs no fence at all, we need to find the dimensions that make the enclosure as large as possible, and then go on to find the maximum area. So what's going on here is we have a wall, and then we want to build a fence along that wall. So we have a total of 1,000 feet of fencing that we can use. And we have one side, I'm going to label it X, the long side of fencing, and then two short sides of fencing that we're going to label Y. Okay? So the goal is to figure out the dimensions that work to maximize that area. Remember, area is length times width, so in this case, X times Y. So we want to maximize, the goal would be to maximize this X times Y equation. Let me rewrite that, sorry. Now, we can't take the derivative of a function with two different variables. We will actually learn how to do that by the end of this chapter, but we can't for now. So we need to come up with an equation. Well, we know that the total fencing is 1,000. So 1x plus 2y has to be equal to 1,000. We don't have a choice there. And then we can solve for one of the variables. Doesn't matter which one. I'm going to go ahead and solve for x just because it would be easier. So we have x is equal to 1,000 minus 2y. So I'm going to plug my x. I'm going to replace my x with 1,000 minus 2y. So my area is 1,000 minus 2y times y, giving us area equal to 1,000y minus 2y squared. And again, the goal is to maximize. Again, anytime we see that word maximize, your option, your brain should automatically go to set up an equation that I can take the derivative of. So I'm going to take the derivative of a, so a prime gives me 1,000 minus 4y, and I'm going to set that equal to 0. All right, if we solve here by subtracting 1,000 and dividing by negative 4, we get y equals 250. So the y value that's going to help maximize this is 250. And we can prove without a shadow of a doubt that this is a maximum number by, again, taking that second derivative. A double prime is negative 4, which means it's always negative, meaning this critical number at y equal to 250 is the maximum. So if y equals 250, that means x needs to be 1,000 minus 2 times 250, which gives us 500. So the dimensions that work for this thing is a dimensions of 250 by 500, and the maximum area is going to be 250 times 500, which gives us 125,000 square feet. Again, the whole goal. Set up your equation. Find an equation that you can take the derivative of to maximize. Anytime the directions say find the maximum area or find the maximum or minimum area or maximum whatever or minimum whatever, the goal is to take the derivative and set it equal to 0. Those critical numbers are key. All right, so let's look at the next example, the last example. The last example is an open top box is made from a square sheet of metal 12-inch. An open top box is to be made from a square sheet of metal 12 inches on each side, and then cutting a square from each corner and folding the sides up. Okay, so we have a square that they're going to cut a thing out of. Hold on just one second. All right, sorry, I turned my phone down. So we're going to cut out some square out of each corner and then fold the sides up. Okay, there's a better picture on page 217 in your book, but this is where I can draw. So I'm going to cut some value out, some x value out of the corner of each thing. And we want to maximize the volume. So volume of the largest box that can be made. So recall, volume, remember, is the length times the width times the height for a box. So let's think about this. The length, and I'm going to write this in blue, the length here and the width, both of those are going to be the same number. We know we started with 12 inches, and then we're cutting off an x value on each side. So it'd be 12 minus 2x. And then if you're folding those sides up, so I'm folding this area up on each side, the height would then become whatever that x value is. So my length and width are 12 minus 2x. And my height is x. In order to take the derivative of this very quickly, we're going to have to multiply it together. So pause the video and multiply that all together. And then I want you to take the derivative. All right, so if you multiplied out the volume function, we end up with v equal to 144x minus 48x squared plus 4x cubed. Then taking the derivative, you end up with 144 minus 96x plus 12x squared, and we set that equal to 0. Okay, when we factor it out, we end up with 12 times x minus 2 times the quantity x minus 6, giving us critical numbers of x equal to 2 and x equal to 6. Okay? Now, if you think about it logically, x equal to 6 will not work. Okay, go back to your picture. If you take a side that's only 12 inches long and take 6 out on each side, you will not have a box. Okay? It would take everything away. So that doesn't work. So the only critical number that we have is x equal to 2. All right? Now, again, we can prove that this is a maximum by taking the second derivative. Let me erase this. So the second derivative of the function gives us 48 no, gives us 24x minus 96, sorry. My brain skipped, okay? By plugging in 2, there's where my 48 came from. We get 48 minus 96, which is a negative 48. It's negative, therefore we have a maximum at x equal to 2. So the volume is maximized at x equal to 2 with a max volume, if we do v of 2, of 128 inches cubed. Again, the goal, anytime we need to maximize or minimize a quantity, set up your formula, okay? And a lot of times that comes from a basic formula that you remember from another class or you remember from another application. Set up your formula, simplify as much as you can, take the derivative, set it equal to 0 to find your critical numbers, okay? Any value, again, that's not in the domain or doesn't make sense for the problem, you can ignore. You don't have to mess with, okay? Take the second derivative at your x value that you want to determine if it's a max or a min to prove that it's a maximum or a minimum, and then plug that value back into your original function to find the maximized value. All right, if you have any questions, let me know.